So I'm going to talk to you about my work in formalizing the C standard. So the C programming language has been around for 60 years now, but it still remains at the center of most of our infrastructure. And it's notionally defined as an ISO standard, which defines a contract between people writing compilers and people using C as programmers. And this standard takes the form of nearly 200 pages of English prose and many more 100 pages if you add the standard library. And as a result of that, it's inevitably imprecise and incomplete and ambiguous. And it's not executable in any way. And it's not only English prose, but it's quite often very subtle prose. And this has been the source of endless debates and confusion even among experts. Typically, you will have three kinds of people who will read the C standard. You will have, on one side, system programmers, like the developers of Linux or FreeBSD, who want to know how to write programs which won't have undefined behaviors and will behave properly on all the architecture they target. On the other side, you have compiler implementers, like the developers of GCC and Clang, who over the years have been implementing overly aggressive optimizations, and they want to know what axioms they can rely on for the correctness of their optimizations. And more recently, you have people writing semantics or static analysis tool who need to know what the standard is. As a result of the fact that the language is only defined as a prose, these three communities have over time diverged in the way they interpret the language and have come to develop disagreement in the way they view the language. So in addition to just really being defined as an ISO standard, C has become defined as the de facto practices of these three communities, which do not match with one another. So there are two ways in which the language is confusing and leads to misunderstanding of what the semantics is. One aspect is the fact that hidden by the C syntax, there is a lot of complexity, like expressions like the one in the center of the slide will have very complicated sequencing semantics. So the graph on the right is summarizing the sequencing of this simple looking expression. You have implicit memory accesses hidden everywhere, and the lifetime of objects can be quite complicated. You have implicit conversions between various integer types, which will have subtle semantic impact. You have partiality because of undefined behavior for many operations, and you have parametricity because of the fact that many aspects of the semantics is implementation defined. And all of these aspects interact with one another in pretty nasty ways. But for most of this, the ISO standard is pretty clear. So if you can manage to read the prose, it is describing what the dynamics of expression is supposed to be. On the other hand, there are aspects of the language which are not actually defined by the standards, either by omission or it's defining something which doesn't actually make sense. And this is mostly to do with memory models. Like the semantics of pointers, in the standard, there are some hints that pointers are more than addresses, and there are some hints at the existence of something called provenance, which is some ghost data hidden in pointer values, but this is never defined anywhere. And you have the same issue with whenever you work with struct and arrays, the standard tells you that you're working on something called sub-objects, but it's never defined anywhere, and so on. So in my PhD project, I developed an executable semantics for a large fragment of C where I tried to reconcile the C language as defined by ISO and the C language as it exists in the heads of C compiler implementers, C developers, this de facto version of the C standard. So for the parts where ISO is clear, the semantics aims to follow it really closely, but for aspects where it isn't, like memory model, it served as a development tool for coming up with new models. And for memory object semantics, this required actually doing empirical study of what are the beliefs of the various people using the C language to try to synthesize a memory model. So to be able to do this, it was really important to have an executable model that could be used as a test oracle. And having an executable model also meant that it was possible to validate the model itself at the beginning of the development by doing differential testing against compilers. to be able to explore designs of memory models, the model was made parametric on the actual semantic definition of the memory model. So most of the definition of the dynamics of C is completely isolated from details about the memory so that you could plug a different memory model while experimenting. And using the executability of the model, you could then compare it against implementation to see if it matches something. To be able to make the complexity of this dynamics of C expression that I mentioned earlier, I opted for semantics by elaboration, where the dynamics, instead of being directly described on the AST of C, is defined as a composition of an elaboration, which is a compositional translation of the C AST into a purpose built language, which is much simpler and much easier to define traditional operational semantics and the operational semantics of this language. So C is really elaborated into a simple first-order functional language, which is typed with like a really strict separation between effectful expression and non-effectful one, and everything is made explicit in the syntax instead of hiding everything like C does. So just to give you a taste of what this looks like, on the left side you have the C standard page describing the semantics of a bitwise shift operator. And you have a bit of syntax at the top, but then most of the definition is really just English text that gives you the typing rules of these operators and then the dynamics of these operators. On the right, you have one clause of the elaboration function which defines the left shift operator in terms of a small program in this core language. And there are some arrows that will show you that, for example, when the C standard says that some operand get their value converted implicitly to some type, you get a call to some pure function in that core language. Okay, so this is how we model the aspect for which the ISO standard is clear. But when it is not, we needed to come up with a model. And to do that, we started exploring, like listing what were the possible design space by just collecting semantic questions and designing a test suite by writing like lots of small programs and questions about it. And then we just went to the C practitioners and conducted 2 surveys. One which was first targeted as experts, members of the C and C++ standard committee, and writers of analysis tools, other experts in the C formal semantics, compiler writers. And we had a second survey which was targeted to a larger audience. And from their answers, we first got like, we identified a particular aspect of the memory model which had lots of disarguments. We could not get like decisive answers. And the focus was really what was the semantics of pointer value and what was this notion of pointer provenance that ISO has hinted at in the past but never defined. So when you think about the semantics of pointers, you can think of 2 extremes. On one hand, you could think of having a really concrete memory model where memory is just an array of bytes and pointers are just addresses. And this is what you used to have in the old days in KNRC, and this matches what the hardware does most of the time. On the other hand, you could want to have a really abstract version of the memory where basically objects are living like in their own island and pointers are kind of opaque. And this is sort of what ISO claims to be describing. Unfortunately, neither of these extremes work for C. You can't have a fully abstract semantics because C allows you to convert pointers and integer back and forth, and it allows you to look at the representation of pointers. And you can't also have a completely concrete semantics because compilers have been doing really powerful optimization based on alias analysis, which make this memory model unsound. Instead, in early 2000, when responding to some question, the ISO committee hinted at the notion that pointers, in addition to their address, have some ghost data that inform how the pointer value was constructed at the beginning of some pointer arithmetic construction, and that compiler implementers are allowed to use this ghost data for their static analysis. But this was never defined. However, because of this phrasing, since early 2000, compiler implementers have been using this wording as license for making more and more sophisticated optimizations which really rely on this never defined notion. So as part of my thesis, I started formalizing a family of memory models called the PNVI memory models, where we try to find a characterization for this provenance. And it was implemented as part of Cerberus to be able to compare like various refinements of this model against compilers to try to find a sweet spot, because you can't really have one perfect memory model because compilers have incompatible understanding of what provenance is, either between one another or even within their own pipeline. So once we had a nice enough memory model, we went to WG14, which is the committee defining the C standards. And in cooperation with them, we made a slightly more complicated version that they liked better than the nicer, more mathematical version, which is called PNVI AUDI. And after many years, it finally got published like a month ago as a technical report by ISO, which is a recommendation for implementers on what provenance should be. And this is, unfortunately, ISO got rid of all the math and just brought back loads of standards, but at least now it's defining what provenance is. And also people can just look at the math version somewhere else. Okay, so I want to conclude on just the Cerberus pipeline, which is the model that was created as a result of all of this work, which ended up basically looking like a big compiler, because if you have something, having something executable is really useful for being able to do experimentation. And just as a result of this, the whole artifact has become useful for many of the collaborators, and a few tools have been built on top of Cerberus. Like you have RefineC, which is an analysis tool for C, which uses the front end, and in Cambridge we have CN and FreeMnet, which uses the whole dynamics of Cerberus. And other people have always also been using the fact that Cerberus is parametric on memory model to explore their own memory models. So if you want to find out more about Cerberus, you can, the project is open source and available on GitHub, and we have more details on our project page. Thank you.